Thank you. Yep. So my name is Hans Rönnbäck, and I work as a senior programmer at Paradox Arctic, or Paradox Interactive. The studio is called Paradox Arctic. And I'm going to talk about designing and implementing a multiplayer network solution. And I'm going to focus mostly on the peer-to-peer aspect of it, but let's begin with the why. Why do I want to create a whole system for this instead of using a readily available solution that you can buy or use an open source version? Well, for us, it boils down to a number of reasons. Hardware independence being one. We can pick and choose which hardware. We do not need to simply support a specific hardware. We can support like the normal stuff like Windows, Linux, etc. And we can also choose to support like consoles, PlayStation, Xbox, etc. Implementing the whole system by ourselves also allows us to control when and what we will support. It also allows for adaptability. We can adapt the network layer for each and every game that we want to do. It also gives us freedom. As we have complete control of the whole system, we can, when it fits us, support new hardware. We can support like bonus stuff like having a cross-platform system in place. We're not locked in by a third party's schedule when they're going to support different platforms. And we also have the ability to allow players on different distribution platforms to play with each other. So when we got this project, we sat down to define a number of goals, what we wanted to achieve with implementing our own system. And a few of those are listed here. Low overhead was really important for us. We wanted to have as little CPU impact, as little memory impact as possible. Also open them up the maximum amount of bandwidth for the payload that the games want to communicate. We wanted the possibility to adapt the network system based on the game that we're going to do. Not all games have the same requirements when it comes to speed or communication stuff. We also wanted to support unreliable communication as well as reliable communication. Again, different games have different needs. If you're going to do a fast-paced action shooter, you're mostly going to use unreliable communication for a lot of stuff, like synchronizing units, etc. And you have some stuff that you really need to be in order and arrive at the destination. And when we were working on Magicka 2, for example, we discovered that on consoles you have requirements, or they tend to want to use their own user context when you're using network features. And games such as Magicka 2, we support gaming modes where you have multiple local players using their own accounts, and then they connect to a game that someone else hosts. So we have a kind of mix of local accounts, and we wanted to have built-in support for that kind of scenario. And that's the complete opposites of most of the PC-based network systems, which are kind of single-user systems. We also wanted another aspect of the multiplayer, multiple user, to be inside the network system, and that is we want to be able to allow people to join as a group into another session. So you get together as a bunch of friends, and together you find a game that you want to join, and you join as a group. We also wanted a simple and easy-to-use API for our developers, so you can integrate the whole system into our own engine, or if you're using a third-party engine for a specific game, we wanted this to be kind of easy to integrate. And we wanted the code to be really well tested. I'm going to go into that a bit more later. So we had a lot of more ideas on stuff that we wanted to support or get into the network system. But it boiled down to a number of problems that we needed to solve. First of all, we wanted to go for a test-driven development cycle. So we needed some kind of test framework. And as we were aiming for using C++, C++11 more specifically, we opted to go for Google Test in the end. Integrates fairly well into Visual Studio. Our build system can integrate well with it. And we get these really nice reports if something breaks, stuff like that. We also needed to abstract much of the system calls and remove the hardware or platform layer. Not all systems support, for example, BSD sockets, especially when it comes to console. They have their own kind of system for doing lots of stuff. Reducing the network overhead, like I said, not only CPU and memory-wise, but also limiting the number of headers that we append to different packets was really important to us. We knew at some point that we needed to address network address translations, or like home routers where you're being hidden behind a firewall of some kind, or using a local IP address that isn't readily addressable for anyone else on the internet. That in turn required us to have some kind of setup to help punch through these NAT devices. So we needed some kind of server system to handle that, so we can exchange information to open up NAT devices. And last of all, we needed a system to handle all these sessions. So when you decide to host a game, you need somewhere to publish the information about the game, about you as a host, so people can kind of find the game that they want to join. Early on in the project, we did a lot of the abstraction, like I mentioned. Not only system calls, we also did a lot of memory management stuff. Like we wanted to be able to make it possible for those implementing or adapting to the network system to use either like pre-allocated buffers, just give them a big blob of memory and we allocate internally from that blob, or if we wanted to use something else. So a lot of stuff, time went into supporting this. As I said, also sockets. Not all systems are BSD socket compliant or use their completely own system, so we kind of needed to wrap that into a manageable little box. We also need to wrap more complex libraries, like handling HTTP or HTTPS requests. That's just a few of the systems that we abstracted and try to kind of have manageable and easy to create create a unified API that we could interface and extend for other platforms as we went along. So initially we also aimed for creating like a hello world version of the network communication. So we had really basic communication initially, mostly to test that all the abstraction, all the memory handling, etc., was working as intended. And we had all these tests that we did due to having a test-driven development cycle. Also, really early, we began to plan ahead what we're going to do next. So one of the things that we looked into was lockless buffers, minimizing overhead. Like we didn't want to copy. If a game creates a bunch of data and they forward it to our system, we didn't want to copy that memory around between buffers. We kind of wanted it locked in, and at some point we knew that we were probably going to need to thread the whole system. So lockless buffers was one of the main things that we looked into. At this point also we began to kind of form the most basic version of the protocol header, including like the version, the length of the payload, and the content type. These are like the most basic things that I think you need in a decent network protocol. And try to illustrate this with a bunch of different colors. We have the basic header with the length and the version. in white over there, and then we have a content header. The content header defines the kind of content. Is it reliable? Is it unreliable traffic that is coming along? We had a field for a channel ID. The channel ID is used to distinguish package not only by session, but if you're in a multi-local user scenario, you can address a specific player on that machine. We had a flag field initially only used to kind of tell if this is a reliable or unreliable packet, and a payload length for that content. Like I said earlier, we wanted to reduce the number of headers, so we implemented a system where we can pack a bunch of game-specific packets. So if the game queues up a number of packets, we try to put them into the same actual packet that will get sent over the internet. And in that case, we just add a length field, prepend the data with length field, and we can have a bunch of different like sub-packets. Again, we wanted this to be optional, so you can turn it on or off or tweak how much data gets appended into the same packet. Then we continued to extend the protocol quite a bit, especially for handling reliable packets. Ended up implementing more or less a minimal TCP version. Not all the fancy stuff from TCP, but the basic like state machine that drives TCP. We mimicked that, and instead in normal TCP you have a window of number of bytes that you can have in there. We reduced that to a number of packets, so we can configure. In this game we support like having 10 reliable packets in there at any point in time. We also got to focus a lot on resend timer and handling read sends when we detect that packets are being lost. And again, we mimicked the system for unreliable packets at this point, so we are able to add multiple reliable packets under the same content header. And in that case, we don't only prepend the length of the packet, but also the individual sequence and acknowledge numbers. And finally, when we bake all this together, if the game uses a number of content systems, like they are sending a bunch of reliable data as well as unreliable, we put them under the same external simple header in white here, and then you can have, for example, unreliable data and then the reliable data in the same actual physical packet, and we can configure that size to work as best between two pairs. So at this point, we had a fairly reliable communication over a local network. You could establish communication, send a bunch of different types of data. We also had a number of debugging utilities at this point to pinpoint, like we had a debug allocators to point out where we had memory leaks, if we were allocating unnecessary amounts of small memory allocations, so we could reduce and tweak that a lot. Also, we simulated packet loss, and simulation of packet loss is super important because it really helps identify lacks in, for example, especially in when it comes to handling reliable packets. So at this point, it was time to kind of move outside the local network scenario and to connect over the internet. So connecting to a game that someone hosts is basically, that consists of the player finding a suitable game to join, looking that up somehow. And in the simple case, there are no firewalls between you and the host. It's just a matter of simply connecting to an IP and port number, very similar to a local network scenario. And the hard case, or the more common case, is that there is some kind of firewall or NAT device present, like a home router, and that is, as I said, it's fairly common, and it presents some challenges in peer-to-peer communication. It's also very similar between IP version 4 and 6. IP version 4, you do not have a public address that people can address you directly at if you're behind a NAT device. You have your private IP. IPv version 6, you have your globally unique IP in most cases, and you can address that, but you may still have a firewall that prevents traffic from going from the outside, from the internet into your local network, unless you first connect to the outside world. So the scenarios are similar, but I'm going to focus on the IP version 4 scenario. So network address translation devices, almost everyone is behind one at this point. And they behave a bit different depending on model and make. A number of different modes that they operate in are the full cone mode, restricted cone, port restricted cone, and symmetric. And I'm going to quickly walk through each of them to kind of illustrate why they pose a challenge when it comes to connecting pairs to each other. So in the best case for a game is that you're in a full cone mode. That means that you have pre-configured NAT devices, more or less port forwarding. You've defined a port on your NAT device, anything that comes in at that port gets forwarded to a specific machine on the inside. This is the ideal scenario. Then you have the address or restricted cone mode. In this case, the client on the inside of a NAT device needs to talk to a server. And at that point, when the package goes from the client to the server, the NAT device creates an entry in its mapping table. It assigns a public port number, and the server that you speak to may answer from the same port that you've spoken to, but it can use any other port as long as the IP address is the same. It will get back to you as a client. Should anyone else try to use the same port, that will simply be dropped by the device. Then you have the port-restricted version, where it works more or less the same. You're further restricted that the one that you're talking to need to respond from the exact same endpoint. In all these modes, something that's important to notice is that when the NAT device allocates your public port, it will keep allocating that port as long as you keep your own local port on your local network and send to someone. It will reuse, just add the new endpoints to that mapping. And then comes the symmetric mode. And in this mode, a new mapping is created for every endpoint that the client talks to. So symmetric is the most troublesome because there is no easy way to kind of predict which port is going to be used on the public side on your NAT device. So, like I said, getting into full cone mode is the desired thing that you want to do. You have a number of techniques that you can use. Universal plug and play, the most common one. You have the Internet Gateways device specification under UPnP. It uses UDP, HTTP, and SOAP objects, and it allows you to kind of open up a port, create a temporary port forwarding rule in your NAT device. Then you have NAT port mapping protocol, introduced by Apple as an alternative to the Internet Gateways device protocol. It's fairly simple. It uses UDP only, super simple protocol to support. And then we have PCP, which is a continuation of the NAT PnP protocol. It features a bunch of different security modes, but if you support NAT PnP, you might as well support PCP because the basics are the same. So using those techniques, hopefully you'll be able to open your port number, and at that point it's necessary to determine in which mode are we. And then you have a few protocols at your disposal to use. Session traversal utilities for NAT, or STUN for short, is a protocol where you more or less send to a known endpoint, asking it to send back packets using alternative ports or alternative addresses, and it also feeds you back what address the STUN server sees you at. So you can figure out if your public endpoint changes depending on which STUN server you're talking to, etc. To further kind of distinguish this, you have net behavior discovery using stun. It kind of separates how your traffic behaves when you're sending out through a NAT device and what the NAT device accepts back in. When we were implementing this, we discovered that some NAT devices have some interesting quirks. Like, for example, if you create a mapping that this client is going to use this port, please forward stuff back to me. Not all devices adhere to this. They accept incoming traffic on this port that you have defined. But when you talk to someone on the other side, you will still get randomly assigned a new port for as your source. We needed to add extra steps to that protocol just to identify such devices. So a bit of the statistics that we gathered initially. So people behind or directly connected to the internet is fairly low, about 2% of our player base. Behind a NAT device is the majority, 93% more or less. And in that case, they are endpoint independent, meaning that they get assigned the same port number whoever they talk to on their NAT device. And the troublesome symmetric devices are at about 4%. So if you fail to open up or create a port forward rule, you need to punch through the NAT device somehow. And punching through a NAT device consists basically of both endpoints or both pairs start sending packets to each other, creating the mappings necessary in the NAT device, and at some point, hopefully, the traffic will go through. Doesn't work for everyone. If you have two symmetric devices that you're behind, there's no way to predict, like I said, the public endpoint for you, so you can't communicate that information to the other pair. So in that case, it's a last resort kind of scenario, use relay servers. So I'm going to walk through a simple NAT punch-through example. In our case, the host that is hosting a game discovered that I'm behind a NAT device. I couldn't create a port forward rule, or it didn't work for some reason. It registers and connects to a negotiation server. Then the client finds the information about the host, and instead of directly connecting to the host, it connects to the negotiation server, and then uses that to communicate with the host, and it tells the host, hey, this is my public endpoint, this is my public IP and port, try to connect back to me. The host in this case can allow that. Yeah, we have a spot left for you, so go ahead, try to connect to me now. The client at that point tries to connect directly to the host, and the host sends packets back. Hopefully, this will work really well, and a mapping has been made in the NAT devices that are present, and you're connected directly to the host. So to facilitate this, we needed some kind of negotiation server. We went for an XMPP solution. It's a well-defined protocol. It's streaming XML. There's a plethora of available server solutions that you can choose to use instead of implementing your own. We added some custom stanzas, like adding our own namespace and handling hooks for our own protocol. Like I said, a host maintains a connection while it's hosting a game. So while clients that want to connect only create a temporary connection to exchange the endpoint information. We also needed to add a custom authentication module to our XMPP server just to handle authentication of players and users. This is an example of the actual request that we send. You send a request to join a specific session, so you identify that by the session ID, and you supply your own ID as the initiator of the request. You also provide information like your public and private IP and port number that the host or the host that you're trying to connect to will try to connect back to. And as we wanted to support joining multiple players at the same time, there's a list of additional player IDs if they're present, so you can do a group joining. So the session, they carry all the necessary information that's needed. The information about the host is the NAT scenario that the hosts are behind, so you can quickly identify, do I need to connect to the negotiation server, or can I use the IPA and port number that the host has? It also contains information like players and game-specific metadata, so the player can use some kind of session browser to find the game that they want to join. And we're using Elasticsearch with a custom front-end to host all these session documents. The session documents are JSON-based, so it's fairly easy to use Elasticsearch as a good storage place for this. So we communicate with a Elasticsearch server over HTTPS. The front end also handles all user authentication, kind of maintains information or maintains the state of the sessions. For example, if a host for some reason disconnects from the internet and can't shut the session cleanly, the front end kind of invalidates the session after a while. And it's also used to find the session, create queries to search for the session you want to join. So creating a session, the host, when you start up a game and you decide to host a game, we create a JSON document containing all this information. It also contains information like different restrictions for the session, the maximum number of players that you allowed, if you have password protection, the visibility of the session, is it public, is it private, or can only friends see it, for example. And then the host publish this document to the document server, so you can kind of find it. We also have a session protocol to handle all the events that are happening when you host a session. Like the requests for joining. Someone sends you a join request, and then we have a bunch of notifications, like when a new player arrives, when someone leaving, or if something changes, game-specific metadata, for example, the maps that is being played or the game mode. So the session protocol uses the reliable channel in our case. Has a small inner header that is specific to the session protocol. More or less a simple flag field message type, which session the packet is destination for, and the length of the payload. And this is a fairly low traffic volume protocol. We only send information about state changes, like I said, players leaving or entering the session, when you propagate session changes and stuff like that. So the payload in this case is JSON-based, and it's fairly easy to just grab the information and integrate and then merge it with the existing JSON document. Using JSON also simplifies things. It's really easy to create new documents or new kind of subfields, and it's more or less human readable, easy to debug. Here's an example of the protocol in action. So you have your outer header, your content header, indicating that this is reliable data, and then you have a session header. In this case, it tells us that it's a leave message. The flag indicates it's a notification type, the length 94 bytes. Its destination is session ID XYZ, and just a plain JSON document. The reason why the player is leaving, and a list of players that are leaving. And back to testing. Like I said earlier, we wanted to use a test-driven development cycle. A good benefit from doing that is that we had unit testing for basically all the code. Our build servers continuously tested all the code. We achieved a really good code coverage. I think we were up at close to like 90% code coverage. The odds in that are like specific network scenarios that are hard to simulate on a build server. And in that case, we relied on normal QA. And during the development cycle, we initially created a diagnostics application. We got a great response from our community. We used this tool to help kind of figure out what we needed to do, how common were different NAT devices, etc. We also created a chat application using this system that was mainly used by our QA, helped us identify a lot of issues, and specifically the hard to identify scenarios, like if you're behind a staggered NAT scenario, which is kind of common if you're on a mobile operator, you have your own Wi-Fi at home and you have a SIM card and that connects to a mobile operator which also does NAT, for example. So the chat application really helped out to identify these kind of specific hard cases. We also created a custom digest script for Wireshark. We used Wireshark very extensively to kind of identify and see that everything went as planned. And so if you're going to do network stuff, I really recommend Wireshark. It lets you kind of see every single byte of your packet, and creating a custom digest scripts just allows us to see more specifically what's happening on a network layer. And it might have been a bit quick today, so this is where I conclude the talk. So questions, more or less?
Thank you very much, Hans. Please, questions?
Hello. I'm not sure if this, like in your case, it was more like co-op games, but like, did you think about the security of like encrypting or signing the actual payloads for preventing some like proxying and taking or changing the contents of the messages?
Yeah, we do have like checksums, for example, on the content of the packets. But it's kind of a way off if the game should handle manipulating or people cheating and injecting strange packets, or if the actual network layer, how much should each do. We're doing basic checksum checks, and then we have the actual user authentication, so we can't kind of manipulate what's on the session servers, for example. You can't change someone else's session and tell them that, there are this and this player, or exchange metadata for that session.
Okay.
Any more questions, please? Okay, so no questions. Thank you very much.
Thank you.